Welcome all. Now we are going to discuss Theorem 7.26, the Weierstrass theorem. Very important theorem. The statement is, if f is a continuous complex function defined on closed interval AB, there exists a sequence of polynomials Pn such that limit n tends to infinity Pn of x is equal to f of x uniformly on closed interval AB. If f is real, then Pn may be taken as real. Okay, this theorem means that if we have a continuous complex function f defined on closed interval AB, we can find a sequence of polynomials Pn such that that sequence converges uniformly to the function f on closed interval AB. If the function is real, then Pn may be taken as real. If the function is complex, then Pn may be taken as complex. Okay, now we will discuss the proof. We have a function f which is continuous and complex defined on closed interval AB. Okay, so without loss of generality, we can assume that the defined interval closed interval AB is equal to closed interval 0, 1. Because closed interval AB and closed interval 0, 1, there is a connection in between them, that is there is a bijection from closed interval AB to closed interval 0, 1 defined by capital F of x is equal to x minus a by b minus a. We can clearly see that the function is 1, 1 and on 2, and checking the images f of a, we get 0 and f of b equal to 1. So we can clearly see that there is a bijection from closed interval AB to closed interval 0, 1. So we can consider closed interval 0, 1 instead of closed interval AB in this theorem. Okay. Also, we are going to assume that f of 0 is equal to 0 and f of 1 is equal to 0. That is, the images of the endpoints are equal to 0. Why we are assuming like this? This is a question. The reasons are in the brackets. Suppose that we have proven the theorem for this case. That is, for the case that f of 0 is equal to f of 1 is equal to 0. Then we can consider the general case. Okay, if we proven the theorem for this case, then that will then we can prove the theorem for the general case like this. Okay, suppose we have proved the theorem for the case f of 0 is equal to f of 1 is equal to 0. Now let f be a continuous complex function on closed interval 0, 1 where f of 0 not equal to 0 and f of 1 not equal to 0. So we are considering f as in the general case. Now consider the function g of x is equal to f of x minus f of 0 minus x into f of 1 minus f of 0. Clearly the function is from closed interval, clearly the domain is closed interval 0, 1. Okay, and also note that here f of 0 is not 0 and f of 1 is also not 0. So by checking g of 0, we obtain g of 0 is equal to 0 and g of 1, that is f of 1 minus f of 0 minus 1 into f of 1 minus f of 0, that is equal to 0. That is, g of 0 is equal to 0 and g of 1 is equal to 0. So g is a function, continuous complex function defined on closed interval 0, 1 for which g of 0 equal to g of 1 equal to 0. Okay, we are assumed that we have proven the theorem for this type of case. Okay, so by what case we have proved above, we can clearly say that there exists a sequence of polynomials Pn such that limit n tends to infinity Pn of x is equal to our function g of x uniformly on closed interval 0, 1. Right? Okay, if we check the function f minus g, we get f minus g of x is equal to f of x minus g of x, that is equal to f of x minus what is g of x? F of x minus f of 0 minus x into f of 1 minus f of 0, that is equal to f of 0 plus x into f of 1 minus f of 0. Okay, from this we can see that f of 0 is a constant and f of 1 minus f of 0 is again a constant. So clearly this is a polynomial in the variable x. That is, f minus g is a polynomial in x. Okay, then we can write f minus g of x is equal to limit n tends to infinity f minus g of x uniformly. because there is no running variable n, so as limit tends to infinity, we can clearly see that limit n tends to infinity f minus g of x is clearly f minus g of x. Okay, the convergence is uniformly clearly. So we can write f of x is equal to f minus g plus g of x, that is f minus g of x plus g of x, where f minus g of x can be written as limit n tends to infinity f minus g of x, and g of x can be written as limit n tends to infinity Pn of x, as we obtained earlier. That is limit n tends to infinity f minus g of x plus Pn of x, that is limit n tends to infinity f minus g plus Pn of x uniformly on closed interval 0, 1. That is, we know that Pn are obtained polynomials, and f minus g is clearly a polynomial, and so we obtained that the function f of x is equal to limit n tends to infinity f minus g plus Pn of x. That is, f minus g plus Pn is a sequence of polynomials whose limit as n tends to infinity converges uniformly to the function f of x. That is, f can be expressed as a limit of a uniformly convergent sequence of polynomials. That is our theorem. So if we have proven the theorem for the case closed interval AB is equal to closed interval 0, 1 and f of 0 is equal to f of 1 is equal to 0, then it is enough to prove the theorem like this. Okay, so we will prove the main part. So it is enough to prove the theorem for the case f of 0 is equal to f of 1 is equal to 0. Okay, so we have a function f which is continuous and complex on closed interval 0, 1. Furthermore, we define f of x is equal to 0 for all x outside the interval closed interval 0, 1. Okay, so the picture will be like this. On the interval 0, 1, that is a continuous function, and outside 0, 1, the function is equal to 0. Okay, and we know that the function defined on a closed bounded interval, that is the function, continuous function defined on a compact interval, is clearly uniformly continuous, and so our f is uniformly continuous on closed interval 0, 1, and by defining f of x equal to 0 outside closed interval 0, 1, we will get f is uniformly continuous on the whole real line. Okay, now we put another set of polynomials. Qn of x is equal to Cn into 1 minus x square raised to n, where n is running from 1 to 3, etc. Here Cn is so chosen that integral minus 1 to 1 Qn of x dx is equal to 1. That is, when we integrate this function Qn of x from minus 1 to 1, we will get the result equal to 1 in such a way that we have chosen Cn. Okay, let it be equation number A. Okay, that is integral minus 1 to n, what is Qn of x? Cn into 1 minus x square raised to n dx, that is equal to 1 for every n. Let it be equation number 1. Now we are going to check what is integral minus 1 to 1 minus x square raised to n dx. Okay, that is equal to twice integral 0 to 1 minus x square raised to n dx, because the function within the integral is an even function. We know that a function is even whenever f of minus x is equal to f of x. Okay, so we can clearly see that the function 1 minus x square raised to n is an even function. So integration minus 1 to 1 becomes twice the integral 0 to 1. Okay, and this is clearly greater than or equal to 2 into integral 0 to 1 by root 10 1 minus x square raised to n dx. The reason is we know that when n runs over 1, 2, 3, etc., 1 is greater than or equal to 1 by root 10, and the function within the integral is a positive function on closed interval 0, 1. So we are only dealing with the positive area, and so we can clearly write as integral 0 to 1 is greater than or equal to integral 0 to 1 by root 10. Okay, and this is greater than or equal to twice integral 0 to 1 by root 10 1 minus nx square dx, and the reason is in the brackets because 1 minus x square raised to n is greater than or equal to 1 minus nx square. The proof is we are considering the function g of x is equal to 1 minus x square raised to n minus 1 plus nx square. Okay, by checking we can see that g of 0 is equal to 0, and the derivative g dash of x is equal to 2nx into 1 minus x square raised to n minus 1. And by checking for x in the range open interval 0 1, we can clearly see that g dash of x, the derivative, is positive. The derivative is positive on some interval means that the function is increasing on that interval. That is, g of x is increasing on open interval 0 1. Since g of 0 is equal to 0 that we have obtained, we get g of x is greater than or equal to 0 on the interval open interval 0 1. If we are considering 0 also, there is no change because g of 0 is equal to 0. The function is increasing on open interval 0 1, and g of 0 is equal to 0. So we have to see that the function ranges over the values greater than 0. That is, g of x is greater than or equal to 0 on the interval. If we are considering 0, then g of x is equal to 0. So in general, g of x is greater than or equal to 0 on the interval. Now, we are not considering the point 1. Okay, that is the function g of x, that is 1 minus x square raised to n minus 1 plus nx square is greater than or equal to 0 on the interval. That is, 1 minus x square raised to n is greater than or equal to 1 minus nx square on this interval. So we are dealing with an integral on this type of interval, like integral 0 to 1 by root n. So in this range, this 1 minus x square raised to n is clearly greater than or equal to 1 minus nx square. So we are replaced this by the formula or by the integral this. Okay, and so we have integral minus 1 to 1 minus x square raised to n dx is greater than or equal to 2 into integral 0 to 1 by root n 1 minus nx square dx. Okay, and we are now integrating the right hand side. We can obtain the right hand side is equal to 4 by 3 root n, which is greater than 1 by root n, because 4 by 3 is greater than 1. So we get okay, let it be equation number 2. Okay, that is what is equation number 2? The left hand side is integral minus 1 to 1 minus x square raised to n dx, that is greater than or equal to 1 by root n. That is equation number 2. Then substituting this in equation number 1, that is integral minus 1 to 1 cn into 1 minus x square raised to n dx is equal to 1. Substituting the result we have obtained, we get 1 is equal to cn into integral minus 1 to 1 minus x square raised to n dx for every n, which is greater than cn into 1 by root n by the equation number 2 we have obtained. That is, cn is less than root n. Okay, that is the equation number 3. Then our qn of x, that is cn into 1 minus x square raised to n, that is less than root n into 1 minus x square raised to n for every n. Okay, now we are considering a quantity delta, positive quantity. For any delta positive with delta less than or equal to mod x less than or equal to 1, we get delta square is less than or equal to x square, that is less than or equal to 1. Taking negative both sides and adding 1, we get 1 minus delta square is greater than or equal to 1 minus x square. And so qn of x is less than or equal to root n into 1 minus delta square raised to n whenever delta is less than or equal to mod x less than or equal to 1. That is equation number 4. Now we are checking the limit of the right hand side of equation number 4. That is limit n tends to infinity root n into 1 minus delta square raised to n. Okay, we have 0 is less than delta square is less than or equal to 1, and taking negatives and adding 1, we can see that 0 is less than or equal to 1 minus delta square is less than 1. So 1 minus delta square is a quantity which is less than 1. So we can take 1 minus delta square is equal to 1 by k, where k is a quantity greater than 1, right? So we are substituting 1 minus delta square is equal to 1 by k, where k is greater than 1, and applying L'Hopital rule, we can see that limit is equal to 0 as n tends to infinity. That is, modulus of Qn of x minus 0 is less than or equal to modulus of root 10 into 1 minus delta square raised to n minus 0. That is, modulus of Qn of x minus 0 is less than or equal to root 10 into 1 minus delta square raised to n, because that is a positive quantity, and so modulus value is equal to that value, which is tends to 0 as n tends to infinity, that we have obtained. Okay, letting mn, that is the supremum value over all x element of closed interval 0 1, we have see that or we can see that modulus of Qn of x minus 0, that is, we have obtained that modulus of Qn of x minus 0 tending to 0 as n tends to infinity. This is true for every x in the interval closed interval 0 1. So if you are taking the supremum, that also satisfies this condition, that is tends to 0 as n tends to infinity. Letting mn to be the supremum, that is mn is equal to supremum over x element of closed interval 0 1, modulus of Qn of x minus 0 is tends to 0 as n tends to infinity. That means that Qn of x tends to 0 uniformly whenever delta is less than or equal to mod x less than or equal to 1 by the theorem 7.9, the MN test. Okay, let it be equation number 5. That is, Qn of x is tending to 0 uniformly in the range delta less than or equal to mod x less than or equal to 1. Okay, now we are setting the polynomials Pn of x, that is equal to integral minus 1 to 1 f of x plus t into Qn of t dt, where x element of closed interval 0 1. Okay, let it be equation number 6, and we are splitting the integral minus 1 to 1 to be integral minus 1 to minus x plus integral minus x to 1 minus x plus integral 1 minus x to 1. Okay, and in the next step we obtain that the first integral and the last integral becomes 0, because the reasons here, because when the running variable t is in the range minus 1 to minus x, adding x on all sides, we get x plus t is less than or equal to 0. That means the point x plus t is outside the interval 0 1. This means that f of t plus x is equal to 0 by our construction of f, that is f is to be 0 outside closed interval 0 1, right? Okay, similarly, when the running variable t runs over the interval 1 minus x to 1, adding x, we get that 1 is less than or equal to t plus x is less than or equal to 1 plus x, that is the point x plus t is outside interval closed interval 0 1 again, and so f of t plus x is equal to 0, and so the first and last integral equal to 0. So we get that this is equal to integral minus x to 1 minus x f of x plus t into Qn of t dt. Okay, now the integration limits is minus x to 1 minus x. Now we have to check whether this Pn is a polynomial or not. For that we have to change the variable like x plus t equal to u, and that is t is equal to u minus x and dt is equal to du. Whenever the running variable t is equal to minus x, we get u is equal to 0, and when t is equal to 1 minus x, we get u is equal to 1. That is, the integration becomes 0 to 1. That is, Pn of x is equal to integral 0 to 1 f of u Qn of u minus x du. Okay, that is, Pn of x is equal to, we are just renaming the running variable u by t. We get integral 0 to 1 f of t Qn of t minus x dt, which is clearly a polynomial in x, because the running limits are integers 0 to 1, upper limit and lower limit are integers, and when we integrate this and we substitute the values upper limit and lower limit for the variables t, we get a polynomial in x. So clearly the Pn's are polynomials in x. The sequence Pn is a sequence of polynomials which are real if f is real. Okay, now we have f is uniformly continuous on the whole real line. So for every epsilon there exists a delta positive such that modulus of f of y minus f of x is less than epsilon by 2. whenever modulus of y minus x is less than delta, right? Equation number 8. We know that f of x is a continuous complex function defined at closed interval 0, 1, and so which is uniformly continuous also, and so f of x attains its supremum value on the interval. Okay, let it be capital M. Let capital M be the supremum of modulus of f of x. Now we have to prove that this sequence of polynomials Pn converges uniformly to the function f of x. Okay, for that we are checking modulus of Pn of x minus f of x, where x element of closed interval 0, 1. Okay, that is equal to modulus of, what is Pn of x? From equation 6 we can write integration minus 1 to 1 f of x plus t into qn of t dt minus f of x. Okay, in the second step we are replacing f of x by f of x into integral minus 1 to 1 qn of t dt, because we know that by equation number A, integral minus 1 to 1 qn of t dt is equal to 1. Okay, so there is no change. This is equal to modulus of integral minus 1 to 1. We are combining the integrals. We get f of x plus t minus f of x into qn of t dt, and in the next step we are taking the modulus inside, and so the equation becomes inequality less than or equal to integral minus 1 to 1 modulus of f of x plus t minus f of x into modulus of qn of t dt, and in the next step modulus of qn of t becomes qn of t, because qn of x is a positive function. And in the next step we are splitting the integration minus 1 to 1 to 3 integrals, like integral minus 1 to minus delta plus integral minus del to delta plus integral delta to 1. Okay, then we can see that the first integral is less than or equal to 2m into integral minus 1 to minus delta qn of t dt plus epsilon by 2 integral minus delta to delta qn of t dt plus 2m into integral delta to 1 qn of t dt, because in the first integral modulus of f of x plus t minus f of x, that is less than or equal to, by the properties of modulus function we can split like less than or equal to modulus of f of x plus t plus f of x, modulus of f of x, and being m with the supremum, we can write this is less than or equal to m plus m, that is equal to 2m. So in the first and third integral this inequality is applied, and in the second integral the running variable t runs over the interval minus delta to delta, so we are checking x plus t, the modulus difference of x plus t and x, that is modulus of x plus t minus x, that is equal to modulus of t, and which is less than delta in the second integral, implies modulus difference of the images of these points is less than epsilon by 2 by equation number 8, that is by the uniform continuity definition. Okay, so this is applied in the second integral, and thus we have obtained this is less than or equal to 2m into integral minus 1 to minus delta. We are replacing qn of t by less than or equal to what, root 10 into 1 minus delta square raised to n by the equation number 4 in the first and third integrals. Okay, the second integral being the same, and we are taking the quantity root 10 into 1 minus delta square is to n outside of the integral, because the running variable is t and this is independent of t, so we are taking outside. We can see like this, and we get the first term and the last term are equal, so we are adding this. We get 4m into root 10 into 1 minus delta square is 10 into 1 minus delta plus epsilon by 2 into integral minus delta to delta qn of t dt. Okay, and this is less than or equal to 4m into root 10 into 1 minus delta square is 2n plus epsilon by 2, because this quantity 1 minus delta is less than 1, and the integral minus delta to delta qn of t dt is also is less than 1, because integral minus 1 to 1 integral minus 1 to 1 qn of t dt is also equal to 1, so this quantity is also less than 1, and 1 minus delta is clearly less than 1, so we can write like this, and this quantity is less than epsilon because we have an epsilon by 2 here, and this quantity where root 10 into 1 minus delta square is to n whose limit as n tends to infinity is 0. So we can choose n to be very large enough so that the quantity 4m into root n into 1 minus delta square raised to n is less than epsilon by 2. So as we are taking n to be so large, we can see that this quantity is less than epsilon by 2, and so this total quantity is less than epsilon. Okay, thus what we have obtained is modulus of Pn of x minus f of x is less than epsilon as n tends to infinity and for every x element of the closed interval 0, 1. Okay, since epsilon is arbitrary, we can write limit n tends to infinity Pn of x is equal to f of x uniformly on closed interval 0, 1. Why this uniformly means this is true for every x element of 0, 1. Okay, so the convergence is uniform. Hence, we have proven that if f is a continuous complex function on closed interval AB, there exists a sequence of polynomials Pn such that limit n tends to infinity Pn of x equal to f of x uniformly on closed interval AB. Okay, if f is real, then we can take Pn may be real. This is the proof. Thank you.